bookmark, we're all good. Okay, so there's a few of these on that worksheet 1 where the antiderivative you're trying to find looks a bit more complex, right, than the other ones that we've been doing. So when I look at something like this, it looks like a product. And we said yesterday, we don't have a product rule for integration. We don't have a quotient rule for integration. For this unit, we're only going to be doing our integration by inspection. We'll look at some other methods in the next unit, but there's no product rule or quotient rule, okay? So if you are going to try to handle this as a product, you won't be able to do that. So the recommendation yesterday that I gave you was, if possible, distribute, right? Always distribute anything you're given. Try to make it a sum or difference of terms. But is that something we want to do with this? You know how I feel about expanding, right? Like we would have to first cube this polynomial or this binomial. I don't want to do that. And then multiply the 2x through, right? So that's not something I want to do. This is a special case where we actually don't have to do that. And this will occur when you have what appears to be either a product or a quotient of polynomials, but the little guy has a special relationship to the rest of the expression. Okay, so if I look at 2x and then I look at x squared plus 5 all cubed, what's the relationship between those two polynomials? Exactly. 2x is the derivative of the inside of that binomial cubed. Okay, so Mr. Fortin, who is my mentor for teaching Math 31, he calls it the baby. Okay, so whenever you see a little expression like this and you've got a little guy, if it is the derivative of the other part of the function, we can consider it to be like a baby function. Okay, and we can just carry the baby along for the ride. Okay, so we can ignore the baby, put the baby in a carrier, bring it with us, but don't worry about it. Okay, the baby is going to work itself out. So we're just going to carry the baby. And we will think about, I don't need to write this, we'll think about just integrating x squared plus 5 to the power of 3 using a power rule. So what would that be? X something cubed. If I were taking the antiderivative of something cubed, what would that become? Something to the power of 4, good, over 4. Now, because this is a composite function, if we think about when we were differentiating it, we would have had to use the chain rule, right? And in the chain rule, we would have multiplied our derivative by the derivative of the inside function. So because we're finding antiderivatives, rather than multiplying, what are we going to do? What's the opposite of multiplying? Divide. So we're going to divide it by the inside of the the derivative of that inside function, which is 2x, which matches the baby. Okay. In differentiating, we would have multiplied by 2x as part of our chain rule. So undoing the chain rule, we're dividing by 2x. Okay. And then the baby just cancels right out. So we have 1 over 4 x squared plus 5 to the power of 4 plus c. Okay, so what looked like it was going to be a problem because it looked like we had a product of two functions wasn't a problem because that little baby function just went away at the end of the day when we undid the chain rule that would have been done to find the derivative. Does that make sense? Okay, you can check it as well. Find the derivative of this. So if I'm finding the derivative, it's going to be 4 over 4 times x squared plus 5 all cubed multiplied by 2x. C just goes away. So it works out. Okay? So for this unit, if you see something that looks too complex to integrate, chances are there's a baby somewhere in there that you can cancel out. Okay. In this next one, again, it looks like a product, right? It looks like something too complex to integrate. I don't want to be doing any cubing of binomials. So I look at that little guy function. Is it the baby? Is it related to the inside derivative. Almost, right? It's kind of like a baby in disguise. So even though it's not exactly like, what would the derivative of the inside function be? 50x to the power of 4. And this is 100x to the power of 4. That's fine, right? Because what is 100x to the power of 4? 2 times 50x to the power of 4. So we can treat this as the baby even if it's got a different coefficient on. Okay? So we'll just carry it along for the ride. Let's find the antiderivative of 10x to the 5 minus 1 to the power of 3. So that's going to be 10x to the 5 minus 1 to the power of 4 over 4 and over what else? 50x to the power of 4. Okay, so it doesn't exactly match the little baby function, but it matches enough to cancel out the x term. Okay, so then when we simplify, I've got 100x to the 4 over 200x to the 4, so that's just going to end up being a half. 10x to the power of 5 minus 1, all to the power of 4, plus c. Molly?
Would you rather us write 1/2 as a coefficient?
Or you can write the whole thing over 2. Either or. Okay? Okay, what do you guys think when you look at example 7? It looks like a quotient, right? Do we have a quotient rule? No. So normally what we would want to do with a quotient is we'd want to see if we could factor it to cancel parts of it out, which we can't. We'd want to see if we could maybe write it as a bunch of separate terms that were all rational expressions, which we can't, right? So we're kind of stuck. Any ideas? What? It's still a baby. It's just a bigger baby, right? It's a healthy eating baby. Okay? 2x plus 3 is the baby of x squared plus 3x minus 1. Okay? So carry that baby along. So we'll just rewrite it. Actually, I'm going to rewrite the whole thing as 2x plus 3. And I'm going to write this as x squared plus 3x minus 1 to the power of negative 1. Okay? That's still something I'm finding the antiderivative of. So I use my integral symbol and I use dx at the end. Okay, I haven't yet found the antiderivative of it, so I'm not yet going to eliminate that symbol. As Trisha pointed out, that's still the baby, so just carry that baby along. How do you find the antiderivative of something raised to the power of negative 1? Natural log, exactly. So it's going to be the natural log of the absolute value of x squared plus 3x minus 1. But then we'd have to divide it by what? 2x plus 3. Okay. If we were working the other way, if we had been differentiating the natural log of x squared plus 3x minus 1, we would have had to multiply it by the derivative of the inside function, right? The derivative of x squared plus 3x minus 1. So in taking the antiderivative, we divide it. And the baby cancels. Baby's gone. So now, here's your answer. Natural log of x squared plus 3x minus 1 plus c. Chad?
Is the absolute value symbol necessary?
Yeah, because your domain has not been restricted, right? There's no, if the domain is restricted in the question and you're told that only x values that result in a positive argument are allowed, then you don't need to worry about it. But if your domain is all real numbers, then it needs to be absolute value of that, right? Because the natural log of a negative number is undefined. You're welcome. Okay, what about B? Negative 1, what's negative? What's this negative out here? That's the baby. Negative 1's the baby there, right? Because we can't multiply it through our square root, right? So we do have to deal with it. But if you look, the radicand is 1 minus x. So the derivative of 1 minus x is negative 1. So this is just another case. It's just a really small kind of baby. Okay? So I'm going to rewrite this as negative 1 minus x to the power of 1/2. And then again, just carry that baby along for the ride. Okay, so negative, this is going to become 1 minus x to the power of what? 3 over 2 divided by 3 over 2 and divided by negative 1. And then that baby will cancel right out. Okay, so your final answer will be 2/3 1 minus x to the power of 3 over 2 plus c. Okay, so that will probably come up a little bit more in the other side of the worksheet. There'll be some that have little baby functions written with them, and you just bring them along. Okay. If your question to me is what if that little function isn't the baby, then I'll tell you next unit we'll learn strategies for handling questions like that. Okay, so for this unit, it will be. Okay, or else we won't be able to integrate it. Any questions right now? So the rest of this lesson just has a bunch, well, except for example 9, I'll do that with you. The rest of it has a bunch of just antiderivatives to try. So let's try these two to start. We'll take those up and then I'll do one more example and then I'll let you guys try the rest. Okay, and then it's just going to be work on antiderivatives, wrapping your brain around it. Okay, it took me a little bit to get myself back into it. We don't have a product rule. Is it a baby one though? No. So it's not a baby. We don't have a product rule. What do? Just multiply it through, right? That's one you can just multiply through. You've got x squared times root x. You can write that as a single x. So that would be your strategy here. So this is an example where this guy is not the baby. Gotta make it
No, it was degree 1. You're right.
But this one's not.
Yeah, so you can't do it. But no, when you do that, it works out.
Because the stays and the difference. What? How are you getting that? Why? How are you getting that?
Oh, man, no, it doesn't because you just times it. No, and then you can't I'm not quite sure. I feel like I am, but now I'm confused with that example. It's not really confusing.
Why? How are you? Guys, what happens when we multiply powers? What do we do to the exponent?
That's right?
That one's
Because
right.
it's
Yeah.
degree 1, or not degree 1, degree 2. But so for this one, it is degree 2, but is it because it's raised to the power of -1?
Yeah,
that
it's
it
like
does
the
that?
inside function is 2, but the whole thing.
Okay. Okay, thank you.
A few of you guys are making this mistake. Remember when we multiply powers, what do we do to the exponents? Add. So it's not going to be just x, right? Were you guys multiplying the exponents? Is that what happened? Yeah, okay. That happens a lot. So we add them. So it should be x to the 5/2 minus 10 sine x. Okay? What is the antiderivative of x to the 5/2? X to the... What's 1 more than 5/2? 7/2 divided by 7/2. Okay, and then this one, -10. If it's -10 sine x, it's +10 cos x plus c. That is my weakest part, is wrapping my head around the negatives and the positives with sine and cosine. It's like you're so used to doing it one way and then you have to undo it. So that's what I get mixed up on a lot. Okay. This one I'm going to rewrite it as 2e to the x minus x to the -2. What's the antiderivative of 2e to the x? 2e to the x. Those are the best ones, right? And then we go -x to the power of divided by -1 plus c. So this will just be 2e to the x plus 1/x plus c. Shh. And the nice thing about this is we don't have to write them over common denominators. We don't have to simplify, okay? Because really, the application with antiderivatives is usually just subbing things in. And having it in a simplified form doesn't make subbing it in any easier, okay? So you guys can just leave these as they are. Okay, no need to simplify. Okay, this example, this is something that happens a lot in sort of higher level math classes where you're sort of guided through the steps of your problem by being asked to do something else. And a big indicator that that's what's happening is when you see the word hence. Okay, so in this one, it's asking us to start by finding d over dx of x sine x. What's that asking us to do? Find the derivative, yes. Okay, so let's start by finding the derivative of x sine x, and there's going to be a purpose to that. So what would I have to use to find the derivative of x sine x? Product rule, exactly. It's going to be x cos x plus sine x, yeah. Okay. And then it says, and hence, so usually when it says hence, it means use what you got from that first part to help you do the second part. So it's asking us to determine the antiderivative of x cos x. So we know the antiderivative of x cos x plus sine x would be what? X sine x. Yeah, we just kind of showed that, right? We found the derivative of x sine x, so it follows logically then that the antiderivative of our derivative would be our original function. Okay? I want to just know what the antiderivative of x cos x is. So whenever we've been finding antiderivatives so far, if we've got sums or differences, we've just been finding the antiderivative of each sum and difference, right? So that's why it makes sense that we could rewrite this as two separate integrals. That make sense? Okay. Great. So then all we have to do is isolate this guy. So the antiderivative of x cos x is going to be x sine x minus the antiderivative of sine x. This is a question where having your notation and making sure you always write your integral symbols until you've actually found the integral is really important, because when I look at what I have to do on the right side to simplify this overall antiderivative, x sine x doesn't have a symbol, so that means I just leave it as is, but I do have a symbol on sine x, so that means I have to do the antiderivative for that, okay? If we had just dropped all our symbols while we worked, we might be confused as to what we had to do in this next step, right? So that's why you don't drop your symbols until you're actually doing the operation. So x sine x, we just leave it as is. What's the antiderivative of sine x? Negative cos x, and then we're subtracting it, so it'll be plus cos x plus e. Okay, so that might come up where you're given an antiderivative to find, like in this one. X is not the baby, right? It's a product, but you're kind of guided as to how you might find it. Trisha?
So is it fine if we just tack the plus C on at the very end?
Yeah. It's totally fine if you tap it on at the very end, as long as you don't forget. Do you guys have it written on your hands yet?
Put it down.
Okay. Do you guys want to take some time? There's a few more to try. They're pretty straightforward. Yeah, I think every one of them you could do. And then there's a summary of those basic rules of integration that we've looked at, and that's really it. The only thing is I will adjust the assignment. I took away question 8. I did it last semester, so I don't actually remember why, but I think I must have had a reason. So just do 6 and 7 from page 408, okay? Maybe not 8. Probably 8 used some integration techniques that we haven't done yet. Okay? So yeah, work on those. I'll put them up in a little bit for you, and then that's it. The rest of the period is yours. Sound good? For those of you with a redox test coming up, you probably are happy that I'm done.